Problem 726 is another turbine problem. However, instead of dealing with superheated steam as our working fluid, we're dealing with liquid water. And so your book makes the point that sometimes if you've got a high pressure stream of a fluid and you have the capability to extract some energy from it, that's fine. And so that's what we're doing here. Also, this would be an example of what might work in a hydroelectric plant, although this is at a much smaller scale. So anyway, we've got liquid water enters an adiabatic turbine at 5 atmospheres of pressure and 15 degrees C. It exhausts at 1 atmosphere of pressure. Estimate the power output of the turbine in joules per kilogram of water if its efficiency is 55%. And then they ask, what is the outlet temperature of the water? And assume the water to be an incompressible liquid. So I've got some information here. My starting information, they tell us 5 atmospheres. And as I mentioned in class, I do not like American engineering units. I like SI units. And so I'm going to convert everything into kilopascals because that's easier for me to figure out, to work with. And I think it's also easier in the steam tables if you use them to work. But that's just personal preference, and it's easy to convert units when you're dealing with MathCAD. So P1, 506.625 kilopascals, 15 degrees C. We could convert that if we need to, but we really don't need to do calculations with temperature here. And then our outlet is just 1 atmosphere, or 101.325 kilopascals. Now, what we can do is we can show you that this problem could be done 2 different ways. And I'm going to show you both ways. I have my preference of what I think is easier and maybe a little bit more accurate, but you'll see that we really get the same answers pretty close for either way. But there's 2 different ways to do this. First, we need to realize that we're dealing here with subcooled liquids. So at 15 degrees C, which is our water inlet temperature, the saturation pressure is 1.7 kilopascals. About 1% of atmospheric pressure. That's really low. Our real pressure is 5 atmospheres, or 500 kilopascals, right? So what this means is this is a subcooled liquid going in, right? You could also look at it from the perspective of, well, at 506 kilopascals, what's the saturation temperature? The saturation temperature is 152 degrees C. Our temperature is 15 degrees C. That's a lot cooler. So maybe that's a little bit easier, more intuitive way of realizing this is a subcooled liquid. Because at this pressure, if it were saturated liquid, it would be 152 degrees C. But it's not. It's at 15 degrees C. That's cooler. So it's subcooled liquid. And then we can pretty much guarantee that whatever is coming out is also going to be a subcooled liquid. I didn't look up the saturation temperature at 1 atmosphere is what? That's 100 degrees C, right? And it is not going to be coming out anywhere close to 100 degrees C, so it is subcooled liquid as well. Now, when we're dealing with subcooled liquids, like I said, there's 2 ways that we can do this. The first way that we'll do it is if we happen to have property tables that include subcooled water. The only problem is we don't in our textbook, and I don't think we do in any of the Perry's handbooks or some of the other kind of very simple online steam tables that you can get a hold of. But there are resources that have subcooled properties or properties of subcooled water. And this is from this website that I uploaded onto the Canvas for you guys to use from this spiraxsarco.com website. And so they give you they give you options for saturated vapor, saturated liquid, subcooled liquid, superheated steam, or mixtures where you have wet steam. So I encourage you to use this. I think this will make a lot of your calculations easier, and we are going to go through that example here just like we did in class. So we're going to use these property tables for the subcooled liquid, and then in the second part of this problem we'll look at the kind of more theoretical way to do this problem. So the energy balance on turbines is pretty much the same as what we've been dealing with all along. It's a open system. We're assuming steady state. This is a very simple turbine, so none of the complexities that we looked at earlier in the semester. Changes in kinetic and potential energy are assumed negligible. This is adiabatic. There's no heat loss, and so the energy balance reduces to the work is equal to delta H, the outlet enthalpy minus inlet enthalpy. And so we're going to do this problem. We're told the inlet temperature and pressure. We're only given the outlet pressure, but remember we're given the efficiency. So we're going to do this just like we do other turbine or compressor or pump problems in chapter 7, where we're given the efficiency, and so the first thing we'll do is we'll do this isentropic calculation, and then we'll use the efficiency to get the real work, and then if we need to calculate the outlet temperature, which we do, we can use that information to back calculate the temperature. So first thing we need to do, we need to get the inlet conditions. All right, so P1 is 506.625 kilopascals, T1 is 15 degrees C. We need to look up the enthalpy and entropy at these inlet conditions. And so what we'll do, I'm not going to show opening the website, but what we'll do is we will go to the website and we will click on the subcooled liquid option, and there'll be a series of little pull down menus. You will hit the pull down menu. We're going to enter pressure and temperature, and we're just going to do a single value. And then what you need to do is you need to enter your pressure unit that you're going to specify your pressure unit. And so our steam table's in our book, and I want you to stay consistent. I would prefer you to stay consistent with how things are done in the book in case you don't have online access and you want to use the book. So this is kilopascals in absolute pressure. So 506.625, and our temperature is in Celsius. So we click on that. The other thing you'll want to do, our enthalpies in our textbook steam tables are kilojoules per kilogram. So you'll need to select pull down menu, select for that. Our entropies are kilojoules per kilogram Kelvin. So the default, I believe, is just joules per kilogram Kelvin. So go ahead and pull down and select that so that it gives you the right units. Once that is done, you hit calculate, and then these numbers will all show up in your table. And so that's what we do, and we simply read off what is the inlet entropy and enthalpy. Inlet enthalpy is about 62.9 kilojoules per kilogram. The inlet entropy is 0.224516 kilojoules per kilogram Kelvin. So those are the inlet conditions. Now we need to do the isentropic case. So to invoke this isentropic operation, we need to figure out where S2, the entropy of our outlet stream, is equal to S1, while P2 is equal to 1 atmosphere. And so if you were doing this with your steam tables, we would go to 1 atmosphere, or 101.325 kilopascals, and then we would scan along to find out where S2 is equal to 0.224516. Now, of course, we can't do this with our textbook because we don't have subcooled liquids, but that's the general gist of what we would be doing. Now, what we can do, though, now that we have the access to this online database, is we can say, all right, I want to find the enthalpy and the temperature for the isentropic case. So I'm going to go to my subcooled steam table tab. I am going to select, hit the little pull down menu. I'm going to input pressure and specific entropy. My pressure is 1 atmosphere, and my entropy, S2, is going to be 0.224516. So I click on that, and I make sure my units are consistent with what I'm entering. So 101.325 kilopascals absolute, 0.2245 kilojoules per kilogram. And then I'm also going to make sure that my units of my output are good. So enthalpy of water, I want that in kilojoules per kilogram because that's what I have up here. And temperature, I want that in degrees C. So that is my temperature there. And so once I have specified the units, I click on calculate, and these values show up. And so what you can see is that our isentropic outlet temperature is 14.9958. So barely changed. It went down a tiny little bit. What about our enthalpy of our output? Isentropic output enthalpy is 62.5475 kilojoules per kilogram. Notice it's not a whole lot different, but it is a little bit lower. So we calculate our isentropic work for this turbine. It's equal to the delta H for the isentropic case. And we see it as minus 0.406 kilojoules per kilogram. So looking at this number, does it make sense? Well, this is a lot smaller number than what we're used to seeing for turbines where we have steam running through it. And that makes sense because we're not dealing with high pressure, high energy steam. We are dealing with water that is at 15 degrees C, which is actually kind of cool. So there's not a whole lot of energy in this water. The other thing, so it makes sense that this number is a little low, and we could even put this in joules per kilogram to have it be 406. But anyway, what about the negative sign? Is that correct? And yes, that is correct, and that's good that we have a negative sign because that means, remember, a turbine is producing work, and so our system is doing work on the surroundings, and that corresponds with what we get from our calculation. So now that we know the isentropic work, we can calculate the real work. We take the efficiency, and remember, in the case where we're producing work, the real work is going to be less than the isentropic work. And so you see with a 55% efficiency, we get a real work of 0.223 kilojoules per kilogram. So again, low number, it's negative, but that makes sense based on what we're dealing with. Now, the last part of the problem asks us to calculate the outlet temperature. Now, we already calculated an outlet temperature, but this is not the outlet temperature for the real case. Right? This is the outlet temperature for the isentropic case. And so if you specified this as your final answer, that wouldn't be quite right. We need to do the outlet temperature for the real case. So how do we find that? Well, we kind of work backwards. We're going to back calculate our outlet temperature from our real work. And so what we do is we use the fact that the real work is equal to the delta H for the real process, right? And so if I were to write that, the real work is equal to H2 real minus H1. So we solve for H2, and we get H2 is equal to the real work plus H1. Now we know the real work, we know H1, so what we can do is we can calculate what H2 for the real case is going to be. And we get a value of 62.73 kilojoules per kilogram. So if we wanted to know the temperature and we had tables, we would look at P2 of 1 atmosphere and H2. We would find out what temperature H2 is equal to this. But remember, we do not have subcooled water temperature property tables. And so again, we can use this online source, which makes things a little bit easier for us, a lot easier for us. And so our inputs, we are going to input the pressure, which is 1 atmosphere. We're also going to input the enthalpy, the specific enthalpy, which is 62.73 kilograms. So we do the pull down menu, select this set of inputs. We then make sure our units are consistent with what we want to input. We type those in. We then make sure our output, we just want temperature. So I'm going to put that as degrees C. And we don't need to know the entropy, but if you want, you can change the units to make them consistent with what we need. But anyway, what we find is after we hit calculate button, we get a value of 15.039 or 15.04 degrees C. And so the temperature of our water, it actually went up by 0.04 degrees C. Is that significant? No, not really. That's a very small temperature rise. There are probably not many thermocouples or thermometers or temperature sensors that are reliably accurate to hundredths of a degree Celsius. So for all practical purposes, the temperature is pretty much the same coming out as it was going in.